So I haven't posted I haven't posted videos yet of last time because I forgot to turn on the mic on this thing. So it was just a bunch of blank. So I went through and chopped it up and did added a kind of narration. So it'll be up soon. But hopefully today I've remembered to turn on the mic. I know I checked it, so it ought to work. And it ought to go up a little bit quicker. So I was going to talk about magnetic problems today, but I thought I'd finish with one that I had for last time, that is an electrostatic problem. And it's just a kind of a complication. In this problem, there are 4 infinitely large sheets that each are charged. The charge density is shown there, sigma 1. So we're looking at it in cross-section. It's a stack of sheets on top of each other. And so this is a very large sheet that runs off the page with a charge density equal to negative sigma. Here's another sheet right next to it, parallel to it, that has a positive charge density that's smaller. And so that's what's going on here. 4 sheets, you're asked for the direction and magnitude of the electric field at 2 different points, point A and point B. And so my first question for you is just, can you use Gauss's law, or are you going to have to do a whole bunch of integrals? So can you use Gauss's law to figure out what these fields are at these points? Remember last time on Tuesday we had at least a couple, well, one problem at least, where you could use Gauss's law for 2 different objects. Each of them had a nice symmetry, and so you could use Gauss's law for those 2. Got about 10 or 15 seconds left, so you want to get an answer in, if you've got one. Okay, so the beautiful thing about the infinite sheet, that 2-dimensional surface that's infinitely big, is that, again, if I look at it in cross-section, if it's infinitely large, then it's symmetric in a lot of ways. In particular, if I rotate around a vertical axis, so if I rotate that sheet around a vertical axis, it doesn't change at all. If I pick a different vertical axis and rotate it around that, it doesn't change at all. So it has all sorts of axes of rotation that are symmetry axes. And because that's true, the field always has to be along that axis. Otherwise, if the field was in some other direction up here, then when I rotated it, that field would change direction and it wouldn't be the same. So the fact that the sheet looks the same when I rotate it around one of these axes means that the electric field has to be the same when I rotate it. And that the only way an electric field vector can be identical when unchanged when rotated around that axis if it points along the axis. So you can use Gauss's law. You can use it all sorts of different ways. Let me just suggest one of them. Suppose you're doing point A. You want the electric field at point A. So you could put a Gaussian surface. You need a closed surface with this kind of symmetry axis. The vertical axis here is the symmetry axis. An appropriate symmetric object would have cylindrical symmetry, since it's rotations around that one axis. So just putting a cylinder in here there will give you something that ought to work for Gauss's law. You can see that the electric field, whatever direction it is either up or down there. It either points up or it points down, depending upon the charge enclosed. And so it's the electric field is parallel to the sides of that cylinder, and so there is no electric flux through the side. I didn't write Gauss's law, but I hope you remember it. There's no electric flux through the sides, but there is electric flux through the faces, or perhaps there is. I know something about, I look at these charged sheets and I can say, well, I know something about them if I, for instance, let's do this. Suppose I make that Gaussian surface the whole distance across all the sheets. These sheets are equal and oppositely charged. So whatever part of the charge is within this Gaussian surface, if there's a positive part up here, there's a negative part down there. A positive part here cancels that negative part. The total charge enclosed has to be 0. And since the fields, if the field is upward there, then it would have to be downward there. Since the trying to figure out the best way to argue this. All right, I'm just gonna do it this way. The top sheet has plus sigma. The bottom sheet has minus sigma. Those two are going to give you opposing field directions when you're up here above all the sheets. They're going to have field directions in the same direction, so they'll add together at point A, and then out here they'll cancel each other again. So the sigma and the minus sigma will cancel out here. And the minus 0.8 sigma and the plus 0.8 sigma are going to have cancellation out here outside of those two plates, and they'll add together inside those two plates. So in each case of those two, outside has E equals 0. And so if there's no charge enclosed and no electric flux, then that's fine for that one. Suppose I go back to this point A. And let me try to erase this, but I'm sure I'm going to erase too much. Nope, not bad. The charge enclosed here, there's no electric field at the top. The charge enclosed here is, well, there's a plus sigma Q enclosed. The area of the face of the cylinder times sigma is how much of it is enclosed due to this upper sheet. The sheet down just below it is negative 0.8 sigma. So minus 0.8 sigma times the same area of the face of this, the bottom face of or the top face of that cylinder. They have the same area. So in other words, the cross-sectional area of the cylinder. So there's a net positive charge, which means there will be an electric field that points down. So the electric field at that point A times the area of that face is, by Gauss's law, is equal to this Q enclosed divided by E0. So that's one way to get that one. There are other ways of getting these, but anyway, you'll find a net downward electric field in the center, and at point B you'll find even bigger downward electric field, because at point B there's no effect from these inner sheets. So I wanted you to think about that one, and you can, I don't think it's a homework problem or anything, so you can work it out on your own. It could easily have been a final exam problem. You can work at it out on your own for practice. But what I wanted to point out was there are 3 important symmetries that are useful for Gauss's law, and we've talked about all of them. There's what you might call 0-dimensional or 3-dimensional object, and that's a spherically symmetric. And charge distributions that are spherically symmetric, you can use a sphere for Gauss's law, for the Gaussian surface. One-dimensional objects are like an infinite line of charge. An appropriate Gaussian surface is perhaps a cylinder around that infinite line of charge. Because it's an infinite line of charge, it has axial symmetry around that axis, around the line itself. If you rotate it around the line, you get exactly the same picture, and so the appropriate Gaussian surface is a cylinder centered on the line, so it has the same rotational symmetry. And then there's the 2-dimensional object. The one we just dealt with is an infinite sheet, and that has an axial symmetry also around essentially any vertical axis if you rotate it. So an appropriate Gaussian surface there is a cylinder or something else, almost anything with a perpendicular, a face here that's parallel to the plane, and a face down there that's parallel to the plane will work. Those 3 kinds of objects have that symmetry that's useful for Gauss's law, for electrostatics. Also fairly useful for magnetostatics, except for this 0-dimensional thing, because to have a magnetic field, at the very least, you're going to need a current in a line. There is no current at a dot. So there isn't this, and there is no magnetic charge. So there is no spherically symmetric current. But there are straight lines, and there are current sheets, and we'll talk about one other kind of symmetric structure that's useful for magnetostatics.